Hello everyone, welcome back to Educase. So today we'll see module 2 and module 2 has energy, chapter 2, rate of reaction. Our lessons are introduction, lesson 2, factors influencing the rate of reaction, lesson 3, the rate equation, lesson 4, and investigation. So I'm going to go straight to lesson 1. Lesson 1 is, in fact, it's just an introduction to the chapter. So the chapter is rate of reaction. So mathematical, what's the rate of reaction? The rate of reaction is a change in the concentration with time. No matter the concentration of which, it can either be the reactant or the product. Consider the reaction in what? You can have the reaction in AUB. As time passes, the concentration of A decreases. The concentration of B increases. Why do physicals reveal that? It simply means that the concentration of the reactant keep on decreasing as time passes. Concentration of the product keep on increasing as time passes. So if mathematically the rate of reaction can be given as rate equals to delta concentration of A and delta T. What is mean of delta? Delta means a change in the concentration. So can I express delta V? Rate can be given as rate equals to delta. That means concentration of A 2 minus concentration of A 1 all around T2 minus T1. If you analyze this guy, you will see that the answer will get us a negative answer. What is the meaning of negative answer? It means that as time passes, the concentration of A decrease. Decrease means we'll have a negative value because it's decreasing. Concentration of B increasing means we're going to have a positive value. So put a negative sign here. We'll put a negative sign. The negative sign does not mean that negative there. Negative sign really means that as time is passing, the concentration of A is decreasing, concentration of B increase. So let's take this more then. You know? The data below to present the change in the concentration of sucrose with time. Perché che la bevi spasso? Filo and concentration of sucrose 80 parts 0.12 0.32 times per second. Concentration is mole per dl. Calculate the rate of reaction. Calculate the rate of reaction. Here, so on the data below, they represent the change in concentration of sucrose. The time. You have time, 3 seconds, 40 seconds. Concentration in mole per dl, 0.4, 0.2. So here we'll be asked to calculate the rate of reaction. So calculate the rate of reaction. So I'm come down. The rate is equal to the solution delta C all over delta T. So we're taking final permutations. Don't forget there's a negative number here. So always put a number. Negative. Okay, don't forget that it's a final concentration minus the initial concentration. The final concentration is created minus T2. 0.2 minus 0.4 divided by 40 minus 6 rate equals to, I mean, 0.2 negative. So you have the negative into negative, all our things will take about the point. The rate of reaction will be 0.2 divided by 20. Answer 0.01. Negative times negative is positive. So adding equals to 0.01 mole per GMK per second. In this case, the rate of reaction can easily be determined. The EL1 is a stoichiometric gradient. In this case, we have a sucrose. As time is passing, the concentration of sucrose keep on decreasing. So we wish to know at the rate at which the concentration of sucrose decreases. It simply means that in every 1 second, 0.01 molar of sucrose is converted. So it can be converted to other products, maltose, galactose, and all the rest. So in this case, we are just focused at the rate at which the reaction does, the rate of reaction proceeds. So example 2, I'm going to give you guys example 2. So this was example 1. So A1. So let's take example 2. So example 2. The rate at which glucose decomposes as food. We have the super time rate in minutes. Concentration of glucose is mole per delta. C'est ça. Mole per delta. Puis on va par séquence. Hence, 0.02, 0.01. Calculate. Calculate. Unit of the calculate units as well. Okay. And about one cable, the example is not quite difficult from what we just seen. The first example was quite similar. This example 2 is also quite similar. So let me give the example to you guys. The rate at which glucose decomposes is as follows. We have a cable that will give it to us. On the table now, the type please 5, 10. Concentration of glucose 0.02, 0.01. Calculate the rate of the reaction. Solution. Your rate equals to delta, negative delta C over delta T. So delta C being the change in the composition. So the other element is exercise. So in this case, implies Rex is equals to negative into 0.01 minus 0.02 or 10 minus pi. So we have negative into negative 0.01 pi. Finding negative into negative 0.01 over 5. How did I get 5? 10 minus 5, that's 5. So having negative is positive. So is that we're having the open door 1 divided by 5. Support for calculator. So we're having 0.01 divided by 5 equals to 2 times 10 to the minus 3 mole per dm cube per liter. So these are the different units of rate. You can express the rate in terms of mole per dm per second or mole per dm per minute, even per hour. So it depends at the rate at which you're working. Is it per second? Is it per minute? Is it per hour? So now we're going to see the rate of reaction and the stoichiometric equation or the stoichiometric balance equation. So now here, let's see how the rate varies in the stoichiometric equation or the balance equation. So rate of reaction and rate of reaction and the balance equation. So consider the balance equation in both. So here we can map the balance equation, right? So the balance equation could get more A plus more B is more C conversely. How does the rate of reaction vary with the different reactants or the different product in the reaction? In this case, we're going to use an equation eligibility for decision of A, consideration of D, consideration of C. And basically, you are in negative 1 over A dA dt equals to negative 1 over B dB dt equals to positive 1 all over C dC dt. In this case, I'm using a differential sign. The differential sign is just telling me a change. But saying differentiation means a change. In this case, we're having negative. You see, if analytics can see that. On this side of the equation, we're having negative signs. On the other side of the equation, we're having positive sign. So in this side, don't forget that in this side, we're having reactants. So here, we're having reactants. Fill up. At time is passing, the reactant are connected to equation. It simply means that the concentration of the reactant decreases. Given that the concentration of reactant decreases, that is why there's a negative sign. A negative sign. So here we relate the rate of one species to the other species. So in this case, we're going to take a simple example. Example. The rate of decomposition. The rate of decomposition of NO2 is 2 times 10 to the minus 3 mole per dmB per 0. Calculate. I want the rate of appearance of N2. A rate of appearance of O2. So this is an example of the part. The rate of decomposition of N2 is 2 times 10 to the minus 3 mole per dm cube per second. Calculate I1. The rate of appearance of N2, I2, the rate of appearance of O2. So this is a question, or this question is a tough question when we call one. You have to first of all write the balance equation. After writing the balance equation, you are going to make use of the balance equation. So let's have a write in the balance equation, yes. So let's have a write in the balance equation.
Vamos a ir in the end.
Balance equation. N2 decompose to give N2 plus O2. Equation not balance. So how to balance the equation? So balance the equation goes first. Yeah, we start the balancing it up to level nitrogen, sorry. I put 2 here. I put in 2 here nitrogen in balance. Oxygen is now, man. So that 2 times K. It's swapped. Oxygen. I put 2 here. So I'm going to put the law that relates M2, N2. I'm going to. So what am I going to have? I'm going to have minus 2 d NO2 dt equals to 1 over 1 dN2 dt equals to 1 over 2 dO2 dt. In this case, I'm maybe used on the trigonometric coefficient. So the coefficients are 2 for N2, 1 for L2, 2 for O2. So what are the trigonometric coefficient? The N2s. This differential sign means the concentration is decreasing. So here, of course, I having 1. But here the coefficient is only 1, that's my 1 over 1, the N2 dt. The coefficient here is 2. I have 1 over 2. If you are critical, you see that for the reactant is in minus, they put up the opposite. Anyone will still calculate the rate of appearance of N2. So, rate of appearance of N2, I just dealing with these two equations, this one and this one. So, Roman 1 will have minus 1 over 2 d N2 dt equals 1 over 1 d LT dt. But this part was given to us in the equation. In the equation, it is given to us as 2 times 10 to the minus 3. So there will be part minus r into 2 times 10 to the minus 3 over 2 d nt dt. So that the nt dt equals to 2 times minus 1 times 10 to the minus 3 moles per dm cube per second. That's one order. So to calculate now Roman 2, we're linking Roman 2, this guy, and another guy there. So Roman 2 is saying that calculate. So minus 1 over 2 d N2 dt equals to, now I deal with oxygen because want to know the rate at which oxygen is appearing. The rate at which oxygen is appearing. So equals to half d O2 dt. Half cancel this. But this guy will be giving, so it's minus into 2 times 10. So you minus 3 equals the O2 dt. So the O2 dt equals negative 2 times 10 to the minus 3 mole per dm cube per second. Mole per dm cube per second. So in this case, we are done the example, so we did wiring, the way you start writing the balance equation. After writing the balance equation, you make use of the stoichiometric coefficient. Very important. Make use of the stoichiometric coefficient. Because if the equation is wrong, everything you are doing is automatically wrong. Because the solving makes use of the stoichiometric coefficient. So now we're going to go to our lesson 2. Lesson 2 is talking about the factors that influence the rate of reaction. Yes, I'm ordinary level stuff there. So we have seen this ordinary level. So here I will just go into this a brief. So a briefing of what you have seen at the ordinary level. So let's see. Lesson 2. So let's listen.
Live. Doctor, look
Factors influencing the rate of reaction. So it's concentration, temperature, solid area. So it's area. Concentration, temperature, catalyst. So these are the four main factors that influence the rate of a reaction. So I'm a condensation, we have the temperature, so like area, and the catalyst. Okay, how the presentation influences the reaction? In this case, we are going to talk about the collision theory. So for the collision, for a reaction to occur, let's see the collision theory. Collision theory. So for a reaction to occur, there should be effective collision between the reactant particle. So effective collision has to be. There's effective collision between a reactant particle. Also, the particle should have a proper orientation. So they have to be oriented properly. And lastly, for reactions to occur, the reactants or the reactant particle need to have a minimum amount of energy. That minimum amount of energy is called the activation energy. So that's what the collision theory is talking about. So the collision theory is summarized into three main points. One, effective collision has to be done. That means the particles have to collide together for a reaction to occur. So the reactant particle should have a proper orientation. Also, for reaction to occur, the particle need to have a minimum amount of energy. That minimum amount of energy is called the activation energy. So, how does the concentration influence the rate of reaction? If the concentration increases, the rate of reaction also increases. If the concentration decreases, the rate of reaction also decreases. Why? An increase in condensation leads to an increase in the number of reactant particles in the vessel or in the container. Given that the reactant particles are more, the rate of effective collision will automatically increase. Okay. If the rate of effective collision increase, it means that more of the reactant are converted into product. Inversely, if the rate of reaction decreases, what will happen? The number of reactant particles it decreases. So given that the number of reactant particles are decreased, automatically the rate of reaction decreases. So that is about the conservation. What about the temperature? Remember, for a reaction to occur, the reactants have to collide together with a proper orientation. An increase in temperature leads to an increase in the kinetic energy of the particle. Given that the particles have more kinetic energy, they will have a high tendency to collide together. So given that the kinetic energy increases, the rate of effective collision will also increase. Therefore, an increase in temperature leads to an increase in the rate of reaction. But if you decrease temperature, what will happen? The reactant particle will have lesser kinetic energy. They have lesser kinetic energy, the rate of collision will drop, and automatically the rate of reaction will drop consequently. So what about the surface area? In your houses, when do you want to cook beans? Usually you use what we call carrot. Carrot is what we call in the butter. The carrot is cooked. So when you add the carrot inside the beans, the carrot go to do a single thing. The carrot is actually a catalyst, but for the catalyst to work, the surface area needs to be increased. Okay, what is the physical significance of that? You use stone camera or you can powder the camera. So powdering the camera, what does that mean? It means that as you are powdering, you increase the number of reactant particles. Given that the number of reactant particles are more, collision will be much more faster, and hence the rate of reaction increase. But if the surface area is small, the rate of reaction will drop. Why? Because the number of reactant particles available for collision decrease. Automatically, the rate of reaction will decrease. Lastly, let's talk about the catalyst. How does the catalyst work? That is why we spoke about the collision theory first. The collision theory, for a reaction to occur, there should be effective collision. And also, there should be proper orientation. And also, lastly, the reactants need to have, or the reacting particle need to have a minimum amount of energy for the reaction to occur. Then how does a catalyst work? A catalyst is just there to decrease the activation energy. Let's say for a reaction to occur, you need to have 10 joules. 10 joules. That's the activation energy for the reaction to occur. The catalyst is going to do that in such a way that it's going to reduce the activation energy even to 5 joules. By decreasing the activation energy, you see that the reaction can easily go or can easily proceed. For the reaction to occur, in 10 joules required. But if you reduce it to 5 joules, so that 5 joules is much more available for the reaction to occur. So the catalyst go to do two things: increase the rate of reaction, secondly, decrease the activation energy. But you have to be very careful. The catalyst is just there to increase the rate of reaction, and it has nothing to do with the equilibrium position. So the catalyst does not affect the equilibrium position. The catalyst goes to increase the rate of reaction and remain unchanged at the end of the reaction. The catalyst can either be a biological catalyst or a non-biological catalyst. Like in biology, you guys saw several catalysts. In chemistry, we mostly deal with inorganic catalysts. So those are the four main factors that influence the rate of reaction. So let me just write a balancing equation in the board. So consider this equation. We have calcium carbonate solid plus hydrochloric acid giving calcium chloride aqueous plus water liquids plus carbon dioxide gas. Carbon dioxide gas. What are the factors that will influence this reaction? We have calcium carbonate, solid, hydrochloric acid, ADOs, giving calcium chloride plus water plus carbon dioxide. Then, why the bottom now influence the rate of reaction? First, the first factor is the concentration of the acids. If initially you are using an acid of concentration 0.1 molar, you simply have to do what? Increase the concentration. Very important. If you increase the concentration from 0.1 to 0.2 molar, the rate of reaction will automatically increase because you have increased the concentration. I've explained how an increase in concentration increase the rate of reaction. Secondly, the surface area of calcium carbonate. You are using calcium carbonate in a solid form. You can also increase the rate by grinding the calcium carbonate, or in the powder, in the marble form, marble chips of calcium carbonate. If you are using marble chips or stones of calcium carbonate, you can grind the calcium carbonate. By grinding, like increasing the surface area and also increasing the rate of reaction. But don't forget that this reaction is done in a reaction basis where you have calcium carbonate plus hydrochloric acid. So you can also increase the temperature of this reaction. If you increase the temperature, you have two types of reactants: the calcium carbonate reactant and the hydrochloric acid reactant. If you increase the temperature, the kinetic energy of the reactant particle increases, and hence they will collide very fast together. The rate of collision increases, and hence the rate of reaction automatically increases. So in a nutshell, that is how these main factors influence the rate of the reaction. Don't forget, the factors are concentration, temperature, surface area, and the catalyst. So let's talk about the catalyst. Let's consider the reaction of both CH4 plus CFT giving CH3Cl plus ACl. UV light. We will have light. UV light here plays the role of the catalyst. So what does that mean? It doesn't mean that in the absence of UV light, reaction will not occur. The reaction will occur, but very slow. So to increase the rate, the speed at which the reaction will go, we usually use sunlight as a catalyst. This is not the only reaction in which a catalyst is used. Remember, in a laboratory preparation of oxygen. So laboratory preparation of oxygen. So see what happened. In lab manganese, you have a hydrogen peroxide decomposing to Madiba water plus oxygen. So during the synthesis of oxygen, you have hydrogen peroxide that decomposes as follows. Hydrogen peroxide giving water plus oxygen. In this case, for the rate of reaction to proceed, we are going to use manganese peroxide as a catalyst. So manganese peroxide is there to increase the rate of the reaction. So I think we spoke about all the factors that influence the rate of reaction, permutation, temperature, surface area, and catalyst. So I'm going to go to lesson 3. Lesson 3 talk about the rate equation.